In the last lecture, I explained about the end condenser method of medium transmission lines. In this lecture, I am going to explain about the nominal T configuration of medium transmission lines. So here nominal T means, if you see the diagram, the network will be of in T shape. Here what is happening means, the total shunt capacitance will be taken as a lumped parameter at this sending end, this midpoint of the transmission line, and the total impedance will be, series impedance will be divided into two halves. So first half is mentioned at the sending end and second half is mentioned at the receiving end. I repeat, the total shunt capacitance will be taken as a lumped parameter at the midpoint of the transmission line, and the total impedance will be divided into, series impedance will be divided into two halves. First half is in between sending end and power shunt capacitance. Second half will be mentioned between this capacitance and receiving end. See the circuit diagram. Here we are taking this half of the series impedance, that is R by 2 and XL by 2 at the sending end, and R by 2 and XL by 2 at the receiving end, and total shunt capacitance is taken as at the midpoint of the transmission line. Current through the shunt capacitance is, charging current is IC. Voltage across capacitance is taken as V1, and sending end current is IS. Sending end voltage is VS. Receiving end voltage is VR, and receiving end current is IR. And sending end power factor is cos phi s. Receiving end power factor is cos phi r. This is how we can get the nominal T circuit for the medium transmission lines. Let us draw the phasor diagram for this nominal T method. First I am taking the VR as reference. See, first I am taking the VR as reference. So VR equals to VR plus J0, and then IR becomes I into cos phi r minus J sin phi r. You can use this equation in solving the problems. So here, as I am taking the VR as reference, see this phasor diagram. First VR is taken as reference, which is OA, and next that VR plus IR into Z by 2 plus JIR into XL by 2, together these gives the voltage across capacitance C. See the equivalent circuit. If you apply KVL for the second loop, your V1 will be equals to VR plus IR into Z by 2. So that is I am going to draw. Now see the phasor diagram. VR plus, how to draw IR into R by 2? For that, first I need to draw IR. Here I am taking the load is of lagging load. So that is why receiving end current IR will be lagging with respect to receiving end voltage VR by some phi r. In that way, I have drawn this IR. Now from the tip of VR, I need to draw IR into R by 2. As it is of resistive drop, which will be in phase with respect to current IR. So IR into R by 2 is drawn from the tip of VR, which is in phase with IR. Now IR into XL by 2 is drawn in perpendicular to IR into R by 2, which will be leading with respect to current IR by 90. Now by adding this VR plus IR into R by 2 plus JIR into XL by 2 gives that V1, voltage across capacitance. Now if you apply KVL for the first loop, your Vs will be equals to V1 plus Is into Z by 2. So for that, here V1 is there. For V1, I need to add Is into Z by 2 means Is into R by 2 plus Is into XL by 2. But for that, I need to draw first Is. For Is, see here, if you apply KCL at that midpoint, your Is will be equals to IC plus IR. So IR is phasor is already there in the phasor diagram. So I need to draw IC. For that, see this equivalent circuit. Your IC is the current flowing through capacitance, and voltage across capacitance is V1. So that your current flowing through capacitance IC will be leading with respect to voltage V1 by 90. So V1 is already drawn. Now from the tip of IR, I need to draw IC, which will be leading with respect to V1 by 90. So that I have drawn that IC. Now by adding this IR and IC, we will be getting the total current IS. Now after drawing IS, from the tip of V1, we can draw IS into R by 2, which will be in phase with IS. And from the tip of IS into R by 2, we can draw IS into XL by 2, so which will be perpendicular to with respect to IS and which is of leading. Now by adding this V1 plus IS into R by 2 plus JIS into XL by 2, we can get the sending end voltage Vs. Now the phase angle difference between Vs and Is is phi s. So this is how we can draw the phasor diagram for the nominal T of the medium transmission line. See there, equations are also there. Capacitive currents IC equals to voltage across capacitance into admittance, that is V1 into j omega c, V1 into j 2 pi f c, and sending end current Is equals to IR plus IC, which is obtained by applying KCL at the midpoint, and sending end voltage Vs will be V1 plus Is into Z by 2. In this way, we can calculate the sending end parameters. Let us go through an example. A 3-phase 50 Hz overhead transmission line of 100 km long has the following constants. Resistance per kilometer per phase is given as 0.1 ohms. Inductance per phase, inductive reactance per kilometer per phase is given as 0.2 ohms. Capacitive reactance per kilometer per phase is given as 0.04 into 10 power minus 4 Siemens. So capacitive susceptance it is given, not the capacitive reactance. Now determine the sending end current, that is Is, sending end voltage, that is Vs, sending end power factor, that is cos phi s, and transmission efficiency when supplying a balanced load of 10,000 kilowatts. So receiving end power is given at a voltage of 66 kV, receiving end voltage is given, power factor of 0.8 lagging, cos phi r is given. So use nominal T method. Let us write the given data. Total resistance per phase becomes as given that in case of problem, resistance is of 0.1 ohms per kilometer per phase, but the length of the line is 100 kilometers. In order to get the total resistance, we need to multiply that value with 100. So which gives total resistance as 10 ohms. Similarly, total reactance will be 0.2 into 100 gives 20 ohms. Similarly, total susceptance will be Y equals to into 100 gives 4 into 10 power minus 4 Siemens. Now, per phase receiving end voltage will be VR by 66,000 by root 3, 38,105 volts, and receiving end current IR equals to P by root 3 VL cos phi r. So 10,000 kilowatts by root 3 VL means 66,000 into 0.8, which gives 109 amperes receiving end current, and cos phi r is given, from that sin phi r will be 0.6, and Z is given as totally 10 plus J 20. Now let us find the sending end voltage. For that, see the step by step procedure. So receiving end voltage is taken as reference. So VR plus J0, that is 38,105 volts, and the receiving end current IR will be IR cos phi r minus J sin phi r, that is 109 into 0.8 minus J 0.6, which will be 87.2 minus J 65.4. Now, by applying KVL for that second loop of the equivalent circuit, already we have written this V1 equals to VR plus IR into Z by 2 in the analysis. So, VR plus IR into Z by 2, V1 is the voltage across capacitance. Putting the values of VR, IR and Z values, we will be getting that voltage across capacitance as 39,195 plus J, 545 volts. After getting the voltage across capacitance, we can find the current flowing through capacitance as charging current as IC equals to J Y into V1. So J into Y means 4 into 10 power minus 4. V1 means obtained as 39,195 plus J 545. So together it gives minus 0.218 plus J 15.6 amperes. After getting the charging current, now we can find the sending end current by applying KCL at that midpoint, that is Is equals to IR plus IC. Now Is equals to IR is already calculated, IC is now calculated. By adding these two, Is gives 87 minus J 49.8 amperes in polar form, 100 at an angle minus 29.47 degrees amperes. Now sending end current will be 100 amperes if you take up the magnitude. After getting the sending end voltage, of course, we need to find the sending end voltage also. The sending end voltage is Vs equals to that V1 plus Is into Z by 2. So V1 is already obtained, Is is now calculated, and Z is already there. Putting the values of V1, Is and Z in that equation, we are getting that sending end voltage Vs as 40,128 plus J 1170. So in polar form, 40,145 at an angle 1.4 degrees volts. So if you find the line voltage for sending end, which will be into root 3, so which will be 69.53 kilovolts. Now if you want to find the sending end power factor, see the phasor diagram. There theta 1 is the angle between VR and Vs, so which is 1.4 degrees. Theta 2 is the angle between VR and Is, which is 29.4 degrees. By adding this theta 1 and theta 2, we will be getting that sending end power factor angle phi s as 31.27 degrees. After getting phi s, by taking cos of phi s, we will be getting the sending end power factor as 0.853 lag. Of course, we can find the sending end power factor angle in the other means also. Just by taking the phase angle difference between Vs and As, we can easily get the sending end power factor angle instead of going for this theta 1 and theta 2. And next, sending end power will be 3 Vs Is cos phi s. So Vs is calculated, Is is calculated, cos phi s is calculated. Putting all these values, the sending end power will be 10,273.105 kilowatts. So after getting sending end power, already you had the power delivered, and your transmission efficiency will be power delivered by power sent out. Means receiving end power, that is 10,000 kilowatts, by sending end power, that is 10,273.105 kilowatts into 100. So transmission efficiency is obtained as 97.34%.